Good afternoon and welcome to the June 23rd edition of the Tuesday webinar series. Today's webinar is entitled Metering Pump Technology. I'm Will Stradling with Siewert Equipment Company, and just a few housekeeping items before we begin. During the presentation, there will be 5 multiple choice questions to answer by poll vote. You'll click on the answer you think is correct. We'll post the results and move on. To receive your operator and PE credit for this webinar, you must complete the poll questions during the presentations. If you run into any technical problems with answering the poll questions, try not minimizing your screen or write down the answers and email them to Sherry. In addition, please feel free to type in your own questions anytime in the questions drop-down arrow, and we'll do our best to answer them at the end as time allows. To receive your PE credit for this webinar, you must complete the evaluation that will pop up at the end. Please stay connected until you complete that evaluation. You will also need to download the certificate of completion and PDF of this presentation. Please note that the water and wastewater credits are still pending. We do not anticipate any issues. However, when we receive the course numbers, we will resend your certificates. That pretty much wraps up the announcements. I'd like to introduce Jerry Conley of Siewert Equipment as our presenter. Please be sure to follow Siewert Equipment on LinkedIn and Facebook to keep up to date on the latest and greatest in our industry. Thank you and enjoy the webinar.
Thank you, Will. That was very professional. Thank you very much.
I tried.
Good afternoon, everybody. I hope everybody is safe and conducting business. It's good to see that New York is entering phase, I guess we're in phase 3, getting ready to go to phase 4. But regardless, I hope everybody is and their families are staying safe. So I'm going to talk for the next hour about metering pumps and metering pump technology. So let's start with some real basics. I know that this is probably a pretty fundamental review for everybody. A couple different types of pumps. Centrifugal pumps. Centrifugal pumps are dynamic. They run anywhere that the system allows it to. I hate to say it, but they're dumb. They run anywhere in the system that the pump will allow it to. So for any given curve, this is the impeller diameter of any given pump, you could be way out here at 4,000 gallons a minute, or you could be running way back here at 40 gallons a minute, depending upon the system curve. Very hard to control that pump. So not a good metering pump, okay? Positive displacement pumps. So 2 things. 1, a positive displacement pump traps a fixed amount of fluid, whether it's in between gears, in a tube, in a diaphragm, between a rotor and a stator. It traps a fixed amount and displaces that fixed amount on every blank being rotation, stroke, okay? So if you look at this curve, say we're down here at 5 feet of head, we're at 14 gallons a minute. If you go up, you maybe have a 6-fold increase in pressure. So now you're up at 30 feet of head, and you've only gone from 12 gallons a minute down to 14. So you can't really say by definition that it's constant flow, but you hear that phrase a lot. So it's not constant flow, but you have a much smaller flow change with respect to the pressure change in a PD pump, okay? And that's demonstrated here. So metering pumps. Metering pumps are PD, positive displacement pumps. A precise or a metered amount of fluid is displaced. Typically, we now measure in gallons per hour, not gallons per minute. Positive displacement, known amount of fluid is displaced. Constant delivery. And then the last bullet, accurate, repeatable, linear. Accurate. Metering pumps typically are anywhere from plus or minus 0.5% to 3%, maybe even 4% accurate. Repeatable means they're 1% accurate today, tomorrow, next week, next month, next year. It's repeatable. And linear means, in the world of metering pumps, as most of you know, there's this issue with turn down. right? You need much less chemical at 3 or 4 or 5 o'clock in the morning that you need at 8, 9, 10, 11 o'clock or 7, 8, 9 o'clock. So that pump might be running at 40 gallons per hour in peak operation, but might be running at 4 gallons per hour or even less at off-peak operation. But you still want that pump to have 1% accuracy down at that lower flow rate. So it's important that, and most of these pumps that we talk about today have known accuracy, are repeatable, and are linear. So you can turn them down and still enjoy the same 1% accuracy or whatever the accuracy is. We just mentioned PD, not uniform flow, meaning a lot of times you need to use a pulsation dampener because you're sending a pulsed flow down the stream, down the discharge. Not all the time. We'll address each technology as it comes up. When you talk about a diaphragm metering pump, and that's what we'll start out our conversation with, it uses a stroking piston to actuate a diaphragm. All right, and we'll talk about both mechanical and hydraulic. And then that lifts a ball check up and you displace an amount of fluid to the discharge. And in most cases, the amount of flow is dependent upon the stroke speed, but in a lot of cases, and with older technology, stroke length. So sometimes you can manually or electrically change the stroke length. With newer technologies, stroke length has kind of become a thing of the past. Will, test question number 1.
Okay. Here we go, launch. Positive displacement pumps. Choose A, B, C, or D.
I don't, Will, do you see it on your screen? Because I don't see it on mine.
I do. About 63% of the vote
Okay.
is in.
That's fine. Good. Sorry. Okay, Will, thank you.
All right. Most of you have voted. I'm going to close the poll. I'm going to share the results. The answer is D, all of the above. Okay.
Back to me, Will.
Back to you.
Typically, my grade school teachers always used to say, usually if there's an all of the above, well, pick that one. Okay, so let's talk about a hydraulically actuated diaphragm metering pump. Sorry about the, I want to move it to about 40 seconds. Okay. So I'm just going to let this run for a minute and then I'll stop it and I'll explain it a little bit. Okay, so here's what we have. We have this hydraulic oil and it's all tan, right? So this piston, and then this piston head, this piston is pushing the oil and there's no air in this oil. So this piston is not physically attached to this diaphragm. So the piston is pushing and trying to compress the oil, which indeed then pushes the diaphragm out. So when the diaphragm is pushed out, this ball lifts up and you have positive displacement. You have the exact amount of fluid leaving the discharge every time. This ball down here, and I'm sorry, hopefully you can see it over the wording, closes. And then when you have the suction stroke, this piston moves back, the diaphragm moves back, this ball closes, this ball opens, and you replace the reagent head with the exact same amount of fluid. All right, piston, all right, goes out, in, and you can see the ball moving. It's big file, so it's a little sketchy. Okay, that's how a hydraulic diaphragm pump works. Now, a mechanical, and I'll focus over here on the left. I hope you can see my arrow. Mechanically actuated diaphragm is just that, where this is your diaphragm here, the black, this is your piston, and you can see that the diaphragm is physically attached to the piston, okay? So whereas in a hydraulic diaphragm, right, you're using oil to compress and push the diaphragm, here it's physically attached to the diaphragm, or I'm sorry, to the piston, okay? That's a mechanically actuated diaphragm. Now, there's some significant differences. Oil barrier, we talked. So the diaphragm acts as a separator and does no work. So in this case, in a hydraulic pump, which is not a hydraulically actuated pump, is rarely used in water or wastewater applications any longer, because they're typically used for higher pressures. So anything you see in a water and wastewater plant can usually be handled by a mechanically actuated pump or some other technology. But regardless, let's say you have a high pressure application and you're pumping 400 or 500 PSI or 1,000, it doesn't matter. You have 1,000 PSI both over on this side of the diaphragm, the process side, and on the oil side. So in theory, that diaphragm does no work. All right, and it moves back and forth in an infinite amount of locations on that diaphragm. So you could have a hydraulically actuated diaphragm pump in a refinery pumping 3,000 PSI, and the diaphragm could last for 15 years. Whereas in a mechanical pump, this is process pressure. So let's say you're pumping hypo at 40 PSI. Everything on this side now, on the mechanical side, is atmospheric. So now you are always against the pressure, and now this diaphragm is always working, okay? So hydraulic pump accuracy about plus or minus 0.5%, whereas mechanical, you're lower, you have to, I'm sorry, it does not apply to higher pressures because you have that pressure balance, that pressure imbalance across the diaphragm. All right, so you're limited really to 350 PSI. And in my opinion, anything over 150 PSI, maybe 200, that's when we like to go up to a hydraulic. Lower initial cost, it's a lot simpler to maintain. You don't have that oil you're dealing with. You don't have all the gearing that you're dealing with, but you sacrifice efficiency or accuracy because that if you look back at this diaphragm, whoops, I'm sorry, right? This diaphragm is affixed right here to the piston, so you kind of have a flex point here, so you don't have that full movement of the diaphragm you have over here. So now you go from 0.5% accuracy to 2, maybe 3% accuracy. Hydraulic and mechanical diaphragm pumps. I just want to focus quickly over to your right. There are some niche applications where we use what's called a hydro tube. It's high solids content, high viscous fluids, where you have, here's your piston, here's your hydraulic oil, and here's your diaphragm. That oil pushes against that diaphragm, which now pushes against all this purple, which is a different oil. And now this tube right here kind of flexes in and out, flexes in and out. Think about holding a plastic tube in your hand and squeezing it, right? And every time you do that, you discharge a certain amount of fluid. So anything that can get through this ball check has a nice, easy pass-through. Rare that we see this municipally, but sometimes on dirty fluids or fluids that fall out, have suspension, they fall out of solution. Solids fall out of solution. This is a really great problem solver. And then we have solenoid pumps. So again, most of you are familiar with it. Pulsatron, LMI is another big name in the industry. It's actually a mechanically actuated diaphragm pump. This piston is mechanically attached to that diaphragm, except it's fired off of a solenoid. It's the lowest in accuracy, but it's the lowest in price. It's some term it a throwaway pump. That's not always the case. Will, test question number 2.
Okay. Number 2, launch. Which of these pumps below are not a positive displacement PD pump? Please select one. About half of the votes are in. Okay, I'm going to close the poll. The answer is B, centrifugal pump. Back to you, Jerry.
Thank you. Okay, so if we just focus on each one of these names down here, all right, blue being a hydraulic actuated pump, orange, I guess, being mechanical, gray being solenoid. Flows, you get the highest flows with a hydraulic actuated pump, okay? Same with pressure. Accuracy, you're plus or minus 0.5%. I'm sorry, this is relative scale over here. I apologize, just a relative scale. So you're 0.5%, 2%, and then something less than that, maybe 3 or 4% for solenoid, okay? Remember that hydraulic diaphragm does no work. So you have once you start the pump, it's a little harder to start up because you have to bleed out any air in the oil. But once you start it up, that diaphragm will last forever. Whereas with a mechanical pump, you're going to have to replace that diaphragm, and the same is the case with a solenoid. Nothing is free in life, so you're going to pay more for a mechanical pump. You're going to pay less for, you're going to pay more for a hydraulic pump. You're going to pay less for a mechanical pump, and you're going to pay even less for a solenoid. And that might be a pretty good scale, right? So if you're going to pay 10 grand for a hydraulic pump, the same pump mechanically might be $4,000 or $5,000. It probably could be half the price. And then again, a solenoid might be 20% of the hydraulic, okay? Solenoid pumps are easy to maintain. Again, a lot of times they're just thrown away, but usually it's just a quick full head replacement, whereas hydraulic pumps are a little harder to maintain because of the work you have to do with the oil and purging air out of the oil. So now let's talk a little bit about advances in diaphragm pump technology, smart technology. This has been on the market for probably, I don't know, 5 to 7 to 8 years. There are several manufacturers that use this or similar type of technology. So I want to go to the second bullet right here. Electromagnets are pulsed one by one. This moves the drive forward one step at a time. So if you look at this little schematic over to the right, these 4 gray blocks, or 3 gray and 1 green and red, those are your electromagnets, and they pulse, and every time you pulse, that motor moves a set distance. The more you pulse, the more it moves. So obviously, if there's a certain number of pulses, it rotates 360 degrees, okay? What this allows you to do, or allows the pump to do, and I'll go back to bullet 1, the suction stroke speed can be controlled independently of discharge stroke speed. This is a big deal in the world of diaphragm metering pumps. Historically, your suction stroke and your discharge stroke are at the same speed, whereas now you can change that, and you can have your discharge stroke at a much slower speed than your suction stroke. And I'll talk in another slide about why that's so important. Okay. So let's take a look at this. I'll let it run through, and then we'll go back and talk about it a little bit. Here's your pump. You have your little stepper motor down here. Now watch, focus right here. Fast, real slow. Fast return, real slow, okay? So the question might be, well, okay, that's great, but so what's the significance of it? okay? So if you're at a normal dosing rate, it may not be significantly advantageous, but where it really comes into play and really becomes advantageous is when you have turn down, and in almost every plant, there's some level of turn down. So I'd like to focus down here. Again, I hope you can see my arrow. And the conventional dosing, this bottom little schematic to the left, all right? At 10%, so you're at 10% of flow, all right? So you're at 10-to-1 turn down. Where did my arrow go? So this right here, the little red square on the bottom, that's your suction stroke. And then your little red box on the top is your discharge stroke, right? Because the suction stroke and the discharge stroke are the same length. Well, now you discharge fluid here, hypo, into your stream, and now you wait and wait and wait and wait and wait because it's such a high turn down. Then you have another quick suction stroke and a quick discharge stroke, and the process goes on. So now you have this phenomena called slug dosing, right? All of this time where you don't have any fluid being injected into your stream. The significance of using a stepper motor is now, if I shift over to the right, now you have this, you still have this quick suction stroke right here on the lower left, the small little red square, but now you can very slowly discharge throughout the entire length of that stroke before you then hit another really quick suction stroke, and then the process returns. So some of the manufacturers make a real big deal about you can get higher turn down, which you can. I've yet to see a plant that actually needs 3,000-to-1 turn down, but the bigger advantage in my mind is that it gets rid of slug dosing, okay? And that's because your discharge stroke is now run independently from your suction stroke, okay? So this is another video. There's 2 or 3 different topics here. We'll just pick one by one, and then we'll watch the video, then we'll come back and kind of dissect it a little bit, okay? Okay. So the first is if you have a blocked discharge, okay? So you're running a blocked discharge, okay? I won't. Okay, so let's go through what, first of all, let me explain this. This is the typical stroke and pressure curve for diaphragm pumps. So on the discharge stroke, you have a quick stroke up, you're giving a constant pressure, and then this is your suction stroke back, okay? Because you will see this several times. This is the screen of the pump that we just saw. This is your set point. So in this case, it's 3 liters per hour. And then what this is right here, this is your calculated flow. So this pump has a it has a differential pressure sensor right here. So it's always measuring pressure differential across this diaphragm. And then it basically runs it through an algorithm, which is in the microprocessor in the pump. And what you're seeing here is a calculated flow. So much as we'd like to say it's a measured flow, it's not really a measured flow, but it's very accurate. And it's always accurate to the set point. So let's go through what we just saw here. Okay, let me go back a little farther. So this is the screen that I talked about. So I'll address this now. So in normal operation, the screen is clear, white. When there's a warning of some sort, there's a visual, this whole screen turns yellow. And again, there's multiple inputs and outputs, so you can send a signal to your SCADA that there's an issue. You can always be alerted of that. And then when there's a significant process upset condition, this screen turns red, and in most cases, it just shuts the pump down. And again, sends an alarm. Okay, so that's let's go back. So what's going to happen here is once the pump very first starts to do a discharge stroke, very first starts the discharge stroke, once it sees this overpressure, right? And this is the whole length of the discharge stroke, your left to right. So you've probably gone 5% of the discharge stroke, immediately senses an overpressure and shuts the pump down, okay? In fact, there was so little discharge stroke that it actually didn't even start to measure flow yet, okay? So you have a blockage in the discharge, it'll pick that up and it'll protect you from it, okay? If you have, this is a discharge line burst, it could be a leak, it could be a suction leak, doesn't matter if it's suction or discharge, okay? Same thing happens. Immediately when you start the discharge stroke, right, the differential pressure, wait a minute, there's no pressure differential where it's supposed to be, right? Because we're relieving all of our pressure up here. So it immediately alarms, there's an issue on your discharge, again, goes into red. And the same would be true on the suction because it is measuring differential, okay? All right, let's watch that again. I'll kind of explain it and we'll kind of pick it apart a little bit. So you have air entrainment, okay? Oh, geez, I'm sorry. If you don't keep this mouse moving, all right, let's get back there. Okay. So you have air bubbles here. You can see the air bubbles on the process side of the diaphragm, okay? So you'll notice here, you're not getting this immediate increase to pressure, to process pressure. You're getting a slow, gradual increase. And that's because this diaphragm is trying to compress those bubbles, right? This is what we refer to as spongy hydraulics. You don't have hard primed hydraulics on your process side, all right? So you're giving that diaphragm work to try to compress those air bubbles. So it finally does, and then it goes to process pressure, okay? Oh, geez, I'm sorry. These are tricky. Bear with me, I'll get right back there. So let me explain what it does. All right, so once it senses those bubbles, and again, it senses it because now you're trying to compress those bubbles, it's actually gonna pick up a pressure differential across that diaphragm. It's gonna know that it's trying to compress those bubbles. So you're gonna see this very quick pulsing of the diaphragm. So it's gonna you're gonna start pulsing really quickly to try to evacuate those bubbles. The other thing that you'll notice when you see the flow, you'll notice that when the bubble, and then I'll run this video again. When the bubbles get into the process side, you'll see the flow go down, right? So the pressure differential calculates the flow is down, and that makes sense because you have air in there. That air is taking up space where fluid should be. So naturally your flow is gonna fall off. And then you'll see that quick pulse. Okay, now I'll be quiet. Now it's pulse, pulse, pulse. You see the flow go up, right? You saw the flow go up. We'll go through that one more time, and I just want to focus on the flow, just on the flow. Okay, this is right? See the flow goes down, something's wrong. Pulse, 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 evacuate the air. Now you're back in line with your set point, okay? So that's obviously the big issue there is off-gassing on hypo. That was specifically developed for hypochlorite off-gassing. Cavitation. You have a restriction or your undersized suction line. I'll run through this all and then we'll take it apart again. Okay, so let's. All right. Oh, gee. I apologize, folks. This is very touchy. If you're not, don't hit it just perfectly. Okay. Okay. So let's say you have a highly viscous fluid, or let's say you have a blockage in your suction, or let's say you have an undersized suction line, right? Cavitation is when, right, you create enough of a pressure drop, typically by friction, but enough of a pressure drop where you drop the vapor pressure, you drop the pressure in the fluid below the vapor pressure of the fluid, and the fluid vaporizes, right? And then once you start putting pressure back on that bubble, that's when that bubble implodes, which, by the way, that's when all the damage happens, like to a centrifugal pump impeller, right? But it implodes. So in this case, right, because you have this big burst of not air entrainment, but of vapor, right, because you're cavitating, you basically have no pressure buildup, right? But then once you start, as you start pushing that diaphragm forward, you get to a point where you collapse that vapor bubble. This is significantly different than air entrainment or off-gassing from hypo. And the pump is smart enough to pick up the difference between the two. So it will compress the bubbles, and then it'll pump. So then, now that it knows that it is cavitating, the pump will automatically move over to what's called slow mode, right? So you set this when you're first installing and programming the pump, you can set this slow mode. So when it picks up cavitation, it'll go into slow mode. And basically what slow mode is it slows the diaphragm, all right? The forward, but more importantly, it slows the suction stroke, right? Because the suction stroke is what's pulling the fluid in, which is what's causing the cavitation. Think about drawing through a straw when you're drinking Coke or Pepsi versus a chocolate milkshake. When you have a chocolate milkshake, it's a much more long, drawn-out suction stroke. Okay, that's exactly what's happening here. By doing that, you lower the pressure loss throughout the suction side of your pump, and you prevent that cavitation from happening. So you're not allowing cavitation, you're basically now preventing it from happening. So it goes in slow mode, yellow turns to green, and you're back off and running, okay? So those are some of the nice features that are a combination of stepper motor technology and then the use of what we refer to as smart technology. Predominantly, the combination of that pressure differential across the diaphragm, which is then inputting into that algorithm in the microprocessor, combined with the stepper motor technology. Now we'll just go through one other thing here. So let me just give a quick description. So remember that first slide showing the curve of the positive displacement pump. It wasn't completely vertical. So there is a change in flow, even though it's small, there's a change in flow with a change in pressure, right? But not nearly as much as a centrifugal pump. But if you think about it, when you're metering, right, very exact, very precise, you really don't want any change in flow at all, right, regardless of pressure. So in a traditional diaphragm metering pump, oh, I'm sorry, I'm supposed to go to maybe like 7 seconds. Okay, there you go. Pressure increases, your flow drops. Pressure decreases over to your right, flow increases. again, with this technology, with that pressure differential, it picks that up. It automatically goes to what's called auto flow adapt, and it will sense the pressure differential, and it will continually be adjusting the running point to match your set point, okay? So some nice features. All right, I might be running a little late, so I better get going. So, smart dosing technology, no slug dosing, nearly continuous dosing because of that fast suction stroke, right? So you're almost always discharge stroking. Solves off-gassing, cavitation, block suction, leaking suction, right? Constant flow independent of pressure. Now you really are getting to constant flow. You don't need to put those in air quotes. Static mixers are great, but with slug dosing, there's a period of time that you're not mixing anything, so they're relatively ineffective, so you don't need a static mixer. And with sampling, again, when you're slug dosing, depending on when you're pulling that sample, you may get a high or a low reading. Now you adjust, and you could be continually moving that adjustment up and down, so you get a much more accurate sample. Okay. Will, test question number 3.
Okay, number 3. Advantages of stepper motor technology, A, B, C, D, E. About half of you have voted. Okay, I'm going to close the poll. The answer is E, all of the above. Back to you, Jerry.
I did warn you about the all above, right? All right, so let's go through a couple other technologies. Let's talk about peristaltic pumps. Whoops, let's talk about peristaltic pumps. Okay. Okay. Positive displacement, right? You're capturing a defined amount of fluid on every rotation. In this case, it's actually every half a rotation, right? And you're sending that downstream. So down here is low pressure. You're developing pressure, high pressure, right? You're basically pinching off that hose in 2 locations. Think of pinching a straw on one, on 2 different ends, and then running those fingers down a 3-foot long straw, right? You're just transferring that exact amount of fluid downstream, okay? That is what a peristaltic pump does. The big advantage of peristaltics started probably 15 years ago. There was not a lot of technology on the market that could handle the off-gassing with hypo. Basically, with a peristaltic, it really doesn't care what you're pumping. Fluid, gas, solids, as long as you can get it in the suction, it'll just push it right through to discharge. So it was a real problem solver for off-gassing. There's since been a lot of different technologies that have also addressed it. I mentioned that we talked about smart pump technology. We'll talk about gear pump technology as well. But certainly peristaltics were the first. Easy to maintain. You just pop the hose out and in, pulls a good suction lift, and usually they have good onboard control options, right? So you can do some of the programming right there on the pump as opposed to in a VFD. Disadvantages. The biggest issue, the Achilles heel for peristaltic pumps is hose life. It's somewhat unpredictable. It's depending on flow, it's depending on hose material, and it's depending on how many rotations per day, minute, hour you have. So that really, the question is not if the hose is going to fail. That hose will fail, right? You're pinching that hose. Take your finger, pinch a straw, and then rub it back and forth on that straw 10 times. Your fingers heat up. You can feel the heat, right? That's exactly the same thing that's happening. So it will fail. So you do have to have some kind of predictive or preventative maintenance program in place so you don't have a catastrophic failure. If that tube breaks, your hypo, that's all over the pump. And then there is somewhat of a pressure limitation, right? The hose gets thicker, stronger, but it has less a less pressure differential, so you're probably limited. I'll take a shot, probably 30, 40 psi. I might be a little incorrect on that, but in that range. Peristaltic pumps. Let's talk about gear pumps. So fluid comes in on your left, low pressure, gets trapped between each one of these gear teeth. You increase pressure, and out the discharge you go. Follow the yellow, the bouncing yellow ball. There we go. Perfect. Okay. This is an external gear pump. So you're not touching here on the outside, and you're not touching here. Both of these are close tolerances. All right. Here you have high pressure. Let's say you have 30 psi, 40, 50. It goes up to 150 psi. You have 100 psi over here. You have atmospheric over here. That wants to go, right? Path of least resistance wants to go here. So it's important that the manufacturer maintain tight tolerances here and tight tolerances here. Let's say you're running this pump and over 7-8 years, you start to see some tooth wear. You start to open up your tolerance here. Now you get what's called slip. So you do get a certain fraction of that flow going back towards suction. When that happens, you have a flow decrease. Typically, that's now seen as a speed increase on your VFD. So the technology that we use, most gear pump technology in the water and wastewater business, is a non-metallic mag drive external gear. So you just saw external, meaning the two gears are outside of one another. The pump is non-metallic and it's a mag drive, and I'll go over mag drive in a second. Resistant to all chemicals. Anything you see in a water wastewater plant can be handled. It too solves the hypo off-gassing. Gear pumps by nature, same thing as a peristaltic. Whatever you get into suction, it'll push over to discharge. And because you have these small teeth and you're capturing much smaller amount of fluid in between each gear tooth, the pulsation is much smaller going downstream, so you no longer need a pulsation dampener in your system. So here's a mag drive. This is an outside magnet right here. It's attached to a motor shaft. That's your magnet right here. All right, and then right here in, I'm going to call this can. This is a containment can. And then inside that can, you have an inside set of magnets. So when the motor starts, this magnet rotates at 1236 RPM. It sends a magnetic flux or magnetic attraction across that can to the inside magnet. And typically this shaft is, sometimes it actually is stationary. It could be stationary or rotational. In this case, you can see this is attached to your impeller. So when this magnet rotates, now you have rotation of your impeller. Again, this is a centrifugal pump. Here's the big deal with mag drives. You see that there's a space here. So this shaft does not penetrate out of the pump, right? It does not penetrate out of the pump. So there's no way for this fluid to leak out of the pump. It is a zero leakage pump. So when you're pumping something that's toxic, that's noxious, that's expensive, that you don't want leaking for any reason, you no longer have to deal with packing or mechanical seals or anything like that, right? Even in catastrophic failure, you still will have no leakage to the environment. And I apologize for the way this picture was taken. It's kind of a stock photo. So let me try to explain, because this is the pump that we have a lot of installations in the state and across the country. So around here would be your outside magnet. It's not shown, right? And then sticking over here would be your motor. So this flange right here, your motor mounts right to this flange, okay? So that magnet rotates. Here is your containment can right here, right? And you can see there's an O-ring mount right there. And then this is your inside magnet. So anything inside this can All of this is all seeing hypo or whatever fluid you're pumping. So that's a magnet right there. You can see it dark. There's a magnet right there. So all these magnets are encapsulated in Teflon, right? Because you don't want the magnet touching the hypo or whatever chemical you're pumping. That magnet has an ID spline, and then a shaft, a ceramic shaft, also spline, fits into that magnet, right? So now you have outside magnet rotating, magnetic flux through the can to your other magnet. This magnet rotates, you have positive engagement, now your gears rotate. Flow comes in, these gears are rotating outside. You catch a defined amount of fluid in between each one of these gear teeth on both sides and discharge out the other end, 180 degrees. This and this are just bearings or bushings, carbon or silicon carbide. And then it's hard to see, but here, this is a liner, and that liner comes across here to contain that flow, all right? That's a non-metallic mag drive external gear pump. So I'm going to show you this video, and then we'll talk a little bit about it. This is our COVID customer demonstration. This is how we have to do it in the new world. There's your liner, and there's your second bearing or bushing, okay? Now, in 99% of the cases where you need to do maintenance on this pump, and historically, you'd have to do maintenance maybe every 5 years, especially if we're running the pump slow. What I have just done to this point is all that you need to do. So you don't even need, the operator doesn't even need to take the pump out of service. You're flanged on either side. You can take the front casing out and access everything from the front, okay? And in almost all cases, these bearings are significantly oversized. They don't need to be replaced. Only if you have high solids and maybe have some teeth wear, you don't need to replace these. Typically, all you need to replace is that liner. That liner simply acts as a protection for this bigger casing, right? So if there is wear, you're picking it up by this sacrificial piece, this liner. I did take the rest of the pump apart just so we could visually see the inside magnet and the containment can. So your head comes off. There's your magnet, and there's your can, okay? And that's what separates atmospheric from your process. 600 PSI burst pressure. All right, mag can go in either way. I'm simply sticking them just to show the engagement, okay? The design, the thought behind this pump was intuitive, meaning let's try it such that you don't need a instruction manual to put it together. Either bearing, it doesn't matter. It doesn't matter what way you put it in, you just put one in. Liner, it doesn't matter which way, it's concentric, just stick her in. You have 2 holes, that's not the right one, then that one is. That gear can be put in either way. Shafts are rifle drilled so you get fluid throughout the pump. Same thing with your second bearing. Even this top head you can put on upside down, doesn't matter, okay? Great for hypo. It really, the biggest advantage, it has all the advantages of a peristaltic. The biggest thing is it solves that Achilles heel, right? It has dry run capabilities, and now you do not have to worry about that limited time on the hose or the tube. The disadvantage, heavy solids and fines. It can pump solids or fines, but you can see those teeth are smaller, so especially compared to a peristaltic, smaller concentration of fines or solids. All right, let's talk about a progressing cavity pump. All right,
Here,
so
just so you know, it's 10 of 1.
yeah, I'm going as fast as I can. Thank you, Sherry. So this kind of gives you a little visual of how this works. This is usually a stainless steel or a metal rotor. and the dark blue is a stationary stator, usually of some rubber compound. And the rotor does touch the stator at these high points. That's what allows you to capture a defined amount of fluid and then move it downstream. The longer the pump, the more pressure you generate. This is an oldie but a goodie, but this does give a pretty good visual of how a progressing cavity pumps. You can see that there's a defined amount of fluid and it goes from cavity to cavity, okay? Really good on high flows and viscosity. Actually, the higher the flow, the higher the viscosity, the pumps like it that much more. Any solids you can put in here, it can pump. It's really great with solids, abrasives, and the smaller sizes, especially on polymer. Most of the polymer injection OEMs will use it for their neat polymer and their dilution applications on a polymer feed system. Will, test question 4.
Okay, number 4. Which is not a feature or advantage of an external gear pump for metering applications? A, B, C, D, or E? Okay, about half of the votes are in. Okay, I'm going to close the poll. The answer is E. Multiple tubing materials. Oh, not an advantage for. Yeah, multiple tubing materials of construction. All right, back to you, Jerry.
No tubing and gear pumps. Got it. All right, let's do a quickie on chem feed systems. Couple of pictures. Okay. Strainer. And it's hard to see, but there's a strainer down here in the bottom left over here. Calibration column here and here. Okay. Pressure gauges. Pressure relief valve is up top. Back pressure valve is down here. Okay. Pulsation dampeners are right here and here. Okay. And some of them may have, this does not have a flow meter. Some may have a flow meter. So the big advantage of a chem feed system is, 1, it saves engineering time. 2, it's single point responsibility. 3, you know, you're working on an $8 million wastewater treatment upgrade. You're putting in an SBR and digester and clarifiers. You know, the last thing I think the contractor wants to be doing is gluing plastic pieces together over in the corner. So by specifying a completely designed, packaged, tested chem feed system, it's just easier on everybody. This is the way not to do it. This is an installation where we actually just sold the pumps and, you know, a customer or a contractor put it together. This was just a piping nightmare. You can't access the pumps. It's bad. So leave it in the hands of the manufacturers that know how to do it. Same customer, just a different system that was supplied by a manufacturer. Nice, the pumps are spaced out more, a lot more room for maintenance. Here's your calc column. In this case, we put in some Rosemont mag meters, just a little more space. So if you have the space, and these are nice little, non-metallic gear pumps that we talked about earlier. So pressure relief, there is usually pressure relief built into each pump, but we always want to put a pressure relief valve in the system to relieve pressure. Remember that positive displacement curve, it just keeps going up and up. It's not like a centrifugal curve where there's a deadhead. So you need to protect the pump and the entire system. And all PD pumps need to run against some kind of back pressure. So putting a back pressure valve in to create some artificial back pressure is the way to go. You can use different types of framing. This is FRP. You can just use that block polypropylene. Doesn't really matter. It's really a quality and a durability perspective. This is a busy chart. My point always with this is the engineer or the owner should push the material selection back on the manufacturer because they have the most experience, especially when it comes to things like hypo. Anything else? A couple of other things for hypo. Vented ball valves are good. Sloping the suction pipe back to suction tank, because if there is any trapped air, you're giving it a fighting chance to drip back up to suction. And we like to do this, stretch a clear pipe, just so you can actually visually see where fluid is or is not flowing. Will, test question number 5, please.
Okay, number 5. Advantages of specifying an integrated chemical feed system. A, B, C, or D? About half of you have voted. Okay, I'm going to close the poll. D, all the above. I'm sensing a pattern.
It's called the easy way out. Thanks everybody for attending. Will or Sherry, I don't see any questions. Are there any questions?
Nope, I do not see any either.
Again, everybody have a great day. Have a safe day. Thanks very much for attending. And as Will said earlier, we have 2 or 3 more of the Tuesday webinars scheduled, and they'll be on our website and on our LinkedIn page. So thanks very much, everybody, for attending. Have a great day.
Thank you, Jerry. Great job.